So I guess you can hear me. So just a gentle reminder, you're going to have the homework submitted by the end of tomorrow, Friday. So the goal of today is we will talk about hypothesis testing, and that is the idea is very similar to the estimation as I have hinted on Tuesday. But anyway, let us quickly review what we learned from the estimation, in particular the interval estimation, because that will be one of the main points that will be useful, right? So instead of going to slide, maybe I just start the whiteboard to highlight the idea that behind what we're doing, right? So let's get started with the what we call population, right? Population is the a collection of the element that we want to study, right? Usually it's the these are the people. We want to look at how, say, the income. We care about the income. We maybe care about how much they spend, right? And say spending or age, so on and so forth. These are the things that we're interested in, right? The best thing, the hope is we would want to know the distribution, right? Maybe you want to know how they looks like, right? Or in the or the histogram, right? This is something we would like to have a look, right? But usually it's hard to obtain this from the population, right? So instead, we usually boils down to know what we call summary statistics, right? That we learn in topic 1, right? That we care about mean and variance in particular, right? And that in the population one, that means the mu and sigma square, right? That the population mean and population variance is one to care. And we are unable to obtain all the data, right? So basically what we do is what we call sampling, right? So basically is we obtain part of the population, which is called sample, right? Or we are sampling, right? Then what we get is sample, right? And if we want to look at the sample, then infer or to guess what happened in population, right? We need this to be a representative one, right? Representative. Okay. And if we want this to be a representative sample, right? We want this. Then we need a random sampling, right? Because when we have random sample, every observation look like what happened in the population, right? In that case, when we calculate x bar and s square, then we can use it to estimate this, right? Estimate, right? And these are all the what we call, maybe I change color, right, to make it a little bit different, right? I change color, maybe I use x bar and s square, right? These are called estimator, right? And they can be used to do estimation, right? Estimation, right? So that is what we have covered, right? And in particular, we talk about these are the point estimators, right? And we also talk about another thing is what we call interval estimator, right? We'll have x bar minus m, right? And x bar plus m, right? And if we know, right, if we know sigma square, right? M will be just Z alpha over 2 sigma over root n, right? If not, then M is just Tn minus 1 alpha over 2 S over root n, right? So that is the thing we covered last time, right? Also, we cover when M, we can decide if I fix the M, I can go back to decide how many N I draw, right? Go back to the question of designing the sample size, right? Just go back one step backward. But that is what we have covered, right? Instead of estimating a point estimator saying X bar, right? We have instead X bar, we go left by M, go right by M, and M is determined by whether you know sigma, right? That is we cover in the last topic, okay? And what we do today, as I said in the very end of the last class, is this, right? We can also use this to answer the question which we talked today is called what we call the hypothesis testing. Right. The main idea is that if we know, okay, mu and sigma, the idea is we know mu and sigma, okay, it implies, okay, maybe I move to the next slide if the, maybe it's okay here, right? If we know mu and sigma, we know X bar according to central limit theorem or large sample, right? We know if I know mu, okay, suppose we know mu, okay, and we know X bar must be look like the bell shape, okay? And if the hypothesis is true, the X bar should be have high probability that is within nearby mu, right? If it is far off from mu, something will unlikely happen, then you would reject the idea the mu belong to the particular number you assign. Okay, let me repeat the statement. This is important. Hypothesis testing on mu is saying that if mu is according to you, you tell me some number, and if the some number is true, then my X bar should have high probability that is between the green region, right? But if figure is outside the green region, that means that what has been proposed should not be, is not supported by data, and hence we will have a second thought, right? We'll reject the hypothesis. Okay, and you probably ask why I use that, right? Very often we want to know, we are given, say, many of you are doing auditing, right, or accounting, then that is something, or the client claims certain thing would happen, you try to guess, right? Or you are a marketing, you talk about quality control, your manager, or you're talking, in that case, you want to check if the quality of your good actually is something what you claim, right? So these are the scenario that you'll be using, okay? And sometimes it's often we use to compare. Maybe I write down what are we doing for the next page. I do hypothesis testing, right? Hypothesis testing, right? The idea is, okay, someone is going to claim mu according to some number, okay, some number, and according to, okay, someone hypothesis like this, right? Someone is then according to central limit theorem or normality, this will be true, okay, and it will be centered at the certain number mu there, right, some number there, okay, and we're trying to say if what you found is belong to this region, which is normal, right? And if this is outside, okay, then we will call it a more or less abnormal, right? And this abnormal anomaly, right? And we will say we will, in this case, we will reject. Okay, we will reject. And that is what happened when we assess a claim, right? So basically, it's just like use the statistics to find whether your evidence to support certain claim or not, right? So basically use statistics to make decision. And how you make this decision is basically reverse of what you have done, right? The reason is like this, right? Because what you're doing was you went to interval estimation is you would be this, suppose this is your sample mean what you found, and you go left by M and you go right by M, right? If this interval include the hypothesis, right? Then actually you would say the data support what you found, right? If it's outside, okay, if it's here instead, right? If I don't know what color I can use, maybe blue, right? If here, right? And I go by M and I go by M, it's not included, right? And that means that it's not there, right? So that means that, as we have seen, this is just the M, right? Same, right? So the idea is similar to saying, from mu, I go left by M, I go right by M. Does this range include the sample mean X bar from the data I obtain, right? If so, the hypothesis is not rejected. If it's outside, yes, you'll reject it. Is that clear what we are doing? Okay, and of course, the M would depend on whether you know sigma or not, right? If the sigma, the M will be just using the Z, right? Because remember, same as hypothesis, right? M will be, if you know sigma, will be this, right? If I don't know, the M will be this guy, right? So that's basically much of what I want to say for the first part of this topic. This is called one sample test, right? Again, that we're saying when we see the proportion, the same idea, right? When proportion, you'll be like this, right? Proportion, that's the one, right? Same idea. Depend on P, one, oh, sorry. The sigma, 1 minus sigma over N over root N. Okay. So it will be something like, it will be like this, okay? And that will be the thing that we are doing, okay? Is that clear? Basically, just like interval estimation, flip it, right? And just try to check the interval include the hypothesis or not. Okay, of course, we'll get to more detail, but this is pretty much what we're going to do for today. Is that clear? Okay. If no, then if okay, then I would just let's see we do the introduction. Okay, so just this slide. Is there any question? I'm done with this whiteboard thing. I'm going to the slide. So this is just overview. I mean, you don't need to worry, but just a high level overview of what we're doing. I mean, once you know the material, this high level thing will be, you can create your own high level overview. Is that okay? Okay, so let us go to the actual stuff, okay, formally. So in hypothesis, we first focus on one sample, and later you see we call two samples. And here one sample is something I said is very useful, right? Because you want to check whether the mean will belong to a certain thing, right? There's a lot of scenario to do it, right? As I said last time, you look at the product, you want to see the product is belong to certain mean, right? There's a product check. But sometimes you also want to look at two samples, which we'll cover next class, next week, is you comparing two samples, whether the mean is the same or not. Which very often used in the real world is like comparing to the treatment group and control group. right? Suppose a marketing manager, and there are one campaign that maybe you're using, say, a famous idol like Mirror to do the advertising promotion, right? You want to check whether Mirror is going to be helpful, right? And you compare to the case where you don't, right? So you need to compare the mean outcome, right? Whether you do it or you don't do it, right? Or you want to compare whether online channel, offline channel, right? Or in your retail market, whether two of them are, which one's better, right? In that case, you do that, right? Or we ask the question, right? Whether, say, people talk about these days, whether vaccine is useful to prevention of disease. They will look at two groups of people, right? One group have the vaccine, one group do not, and see how many of them have the disease, right? So these are the comparison between two different samples, and that will be something we'll cover next week. And the week after is ANOVA. Actually, it's compare more than one treatment, right? We talk about whether you vaccine or no vaccine. ANOVA. In the next topic, it's about multiple treatment, right? You can have vaccine A, vaccine B, vaccine C, vaccine D, and you compare different treatment will have different, whether they have different impact, right? So that's why this is a highlighting what's going on in the next one, right? And actually, the last topic also related to what we are doing. Instead of a treatment is A, B, C, D, we have some continuous treatment, right? We can talk about treatment is going to be a, say, amount of vaccine you're using, right? 5 ml, 10 ml, 20 ml, so on and so forth, right? When the continuous treatment, then it's a regression we are doing. So basically, it's the main thing about the rest of the course, okay? But anyway, let's start. So we need to learn some terminology before we proceed, because hypothesis testing is a very complicated objects, and actually what we cover is just a very small tip of the iceberg, but they have their own terminology, so we have to learn it, okay? So the main idea of hypothesis testing is we are going to test a claim, okay? A claim is a statement on the population, okay? Use a parameter, right? Say, in our case, we say mu is equal to 4, right? Or say sigma is equal to 5, something like this, okay? Something like that. Or even more general, mu is more than 4, so on and so forth, which is a claim, okay? And we will call this claim H null, which is a notation we're using. And this is, if the claim is the thing we're given, it's called null hypothesis, okay? And quickly you would ask, what is null hypothesis? It's something that coming from historical evidence or prior belief, or the client tells you, okay? And that is called null hypothesis. It's something that if you don't have the data, this is what you believe, okay? It's like the prior belief, right? Prior. It's a prior belief, or what we call the working assumption, right? And here is, we have another one we call alternative hypothesis, okay? And this is the claim that you would hold if the null is being rejected, okay? And that is something like if you drop what the prior belief, this is what the alternative you should have, okay? This is called H1, okay? And obviously, these two are mutually exclusive, right? Mutually exclusive, because if you reject H null, it must be H1, okay? But they need not be exhaustive, okay? So it means that they need not be complement to each other, okay? Later you will see what I'm saying, but in our yeah, but you see what do I mean by mutually exclusive? Well, not they why they are not exhaustive, but so what is the logic there? How do we evaluate this based on data? The idea is the following. Okay, the claim is let's like the common law idea. Okay, this is our prior belief, right? In the courtroom, you would assume the defendant is not guilty until evidence told beyond reasonable doubt the defendant is guilty, right? So you need to beyond reasonable doubt. So the same idea here, we assume the null is correct, okay? And we look at data, okay? If data tell us, is it beyond reasonable doubt, okay? That you would say it can't be right, right? Though that's the idea as I beginning talk about. If I claim is the X bar, right? The mu will be actually look like the bell curve according to central limit theorem, right? If you have large number, large sample size, right? Then it should highly likely beyond here, right? And you will say this hypothesis will be reject if it is far beyond on the other side, that is beyond the reasonable doubts, right? You reject the data is not support what you claim, then you reject. Okay, so that's the idea. If it is too far away from mu, then we will say no, right? And how far is far away depends on probability, right? Because you ask how far is far away, how do you quantify this in probability, right? It's in terms of this area, right? It's not in terms of absolute distance, but rather in terms of probability. Okay, is that clear what we're doing? Okay, I hope that's clear. Is that okay? Because this is a rather important concept. I hope I convey the message. Okay. In our class, okay, we would only focus on the case what we call simple hypothesis. Okay, and which means that we are saying the population parameter is equal to particular value. Okay, equal to 3, equal to 4, equal to 5, equal to 0. Okay, so that is a thing we are talking. And in general, okay, you can talk about composite hypothesis, okay, which is talking about within some interval, okay, like inequality is an interval, right? Or it can be like mu is between maybe I use this not use this notation, right? Maybe just talk about say mu maybe between 5 and 3, okay? This is also a composite hypothesis, right? But these are the things way beyond what we are covering, okay? So we just focus on the case, we just test very simple, which is also very often used in the real life, is test whether equal to a certain number, okay? And that is why null is always simple, okay? And our alternative is always composite, okay? When I say mu not equal to 3, okay, it's a composite, right? Because it will be left-hand side and right-hand side, right? It's an interval, okay? So that would be the idea, okay? So we have hypothesis testing, we have null hypothesis, alternative hypothesis. Now we have simple and composite. So there are 4 items here. Is that clear? Okay. So in our case, we just have simple null and composite alternative. Okay, so that is the cases we want to focus on. Okay, and if you want to know more, it will be beyond our class. Okay, it will be something you learn in more advanced class. But as far as I can tell, for me, I mean, I just use this simple case. Okay, even for my own research, I don't actually go beyond that. Okay, I think that is this will be the most case you will be encountered unless you are doing a very specialized field that require you to do more than that. Okay. So I mean, yeah, as I said. So here we talk about a hypothesis, and sometimes you will see the further distinguish, we call one-sided or two-sided. Okay. So when we talk about, say, mu is less than 3, or mu is more than 3, maybe more than 3, not equal to, more than 3 and 3, that is called one-sided. Okay, because it's one side once and for all, right? It's just one side is like a line there, right? One side means you go right or you go left, right? So that is it. That is that's the idea, right? Bigger than some number, smaller than some number, one-sided. Okay. And two-sided means that like this, mu not equal to 3. Okay. And why two-sided? Because this is 3 is here, right? You talk about this and this, right? Both sides, right? You go two-way extreme, it's also valid, then it's two-sided. Okay, so that is the difference. Okay, so that remind you several things. We have null hypothesis, alternative hypothesis, simple hypothesis, composite hypothesis, two-sided hypothesis, and one-sided hypothesis. Okay, I know that a lot of terminology, but I mean, because this is a complicated object, so we have to learn those. I mean, that is not because they will make our discussion more convenient. Okay. And later, probably I'll explain why you need these 3, or maybe I can talk about it now. Okay. But probably you may ask why you would have these 3 choices, right? And let's talk about why these 3 are important. Okay. So suppose you are consider application of you are a food manufacturer. Okay. You're doing quality control. Okay. And you're talking about a food. Okay. And talk about the food, say you're talking about, say, a dry mango. Okay. Dry mango would be the active ingredient is mango, right? And maybe you mix certain thing there, you mix some sugar and mix some other seasoning there, right? You want to make sure that your dry food has enough dry mango there, right? Not too much seasoning, right? In that case, you would be worried about, okay, if you would be not happy, right? If the dry mango or the active ingredient in your food actually too little, right? So the consequence of having less than will be an issue, right? If your thing has more, no one worry about it, right? Or in other words, maybe other example would be you talk about your food. Your food has, say, you claim the content have 1 kg, right? And if your product has more than 1 kg, no one would jump up, right? Less than that, then people would complain, right? There's no consequence of more than, there's consequence less than, then you will use this one. Okay. And similarly, if you talk about your food, your product is a food, the right food, and then you talk about whether you have too much harmful material in the food, right? If your food has too much harmful material, people will get sick and you get sued, right? So that's why the bad consequence is coming from more than, then you would use this one. Okay. And say when you would use this guy, okay, when you use the not equal to, is when violation on both sides will have bad consequence, right? As an auditor or accountant, you go to audit, you go to check the inventory or check the banks, right? Check the, say, suppose the company claims they have certain amount of cash or deposit, right? You want to make sure that this is exact amount that they have, right? You don't want to have more than or less than, right? So that is the case where you want to equal, okay? So whether which one to employ depends on whether which would have a bad consequence, right? If more than or less than is a bad consequences, you use two sides. If only less than is a problem, you use less than. If only more than is a problem, you use more than. Okay? It really depends on consequence. Okay? It also really depends on whether you know from the data that is possible or not. Right? Say you want to check the data is how many people the hypothesis is that no people is say is okay, or number of hours spending on watching bad thing online. Okay, so you want to test hypothesis no one in CHK is watching bad thing online. Okay, and in that case the hour, right, is not going to be negative, right? It's either 0, right, or positive, right? In that case, you only use one-sided, right? So the data would determine whether you would have one-sided, or from the consequences you use one-sided or two-sided. Okay, is that clear? Okay. Anyway, you see the application, then probably you will give you some more idea. Okay. Well, I guess that is what I said, right? Whether two-sided is whether you have no knowledge which side, or whether division is important, as I mentioned already, right? If depends on the application. Okay. And less than or more than, and you know what alternatives would be. Usually it's driven by the theory. Okay, tells you whether not, right? Because say suppose you're comparing later, you compare say whether you do marketing, right, or don't do marketing. You should expect doing marketing should be helpful, right? Should be one-sided. So so that is the idea of one-sided alternative hypothesis. Okay. So again, there's some more terminology. I'm sorry, but that is required. So in general, this also in general is about making error in making decision with data. Okay. So actually you learn that type, probably some of you may learn there's type 1 error and type 2 error. Okay. The idea is, okay, if you wrongly reject certain thing, that is called, if this is true, then now it's true, you still reject it. Okay, it's not type 1 error, that's alpha. Okay. This alpha is indeed same as what we learned in the last class. Right? Remember X bar is here. We have a bell curve here. Mu is here, right? Remember what we learned last time. We're similar to what we learned. We said confidence interval is 1 minus alpha, right? So the two sides alpha, right? Because if you are trying to reject on this region, right? Even this is true, with alpha probability they will end up there, right? So even the sampling mistake, you would end up in the extreme regions. So that's why even if it's true, you will still reject it. Okay, it's alpha. So alpha is something that we have to decide what they are. Okay, is by choosing the alpha, we decide how to test it. So this is our choice. At the end, it's our choice. It's our choice. It's our choice. Okay, we choose what is the alpha, and the alpha we determine how we do the test. Okay, we can make it bigger or make it smaller. Okay, same as the interval estimator, right? We can decide how big is the interval, right? We decide the alpha, right? So this choice. The second one, of course, is related to the reverse case. If it is false, we fail to reject. This is beta. Okay, and in some sense, okay, they are trade-off. Okay, by choosing a smaller alpha, we will have used a bigger beta. Okay, so the choice of what you're doing is going to be a trade-off between the two. And usually because we don't know what happened when this is false, okay? So that's why we will directly choose alpha, okay? Beta will determine implicitly, okay? We will not actually do the calculation, okay? But we will talk about the choice of alpha, okay? Alpha, as we said, right, all of time, like the last class, we will talk about alpha. Our choice usually is like 1%, okay? So 10%, 5%, or 1%, okay? Alpha, this is the three standard numbers, okay? And very often, you will see this terminology very often, you call power of test, okay? Power of test is whether you got a good judge, right? The good judge will tell you if the defendant is guilty, right? If he's guilty, then he's able to charge them, right? It's whether the judge is smart enough to tell, right? Or the prosecutor is very powerful, right? With a powerful prosecutor, so we can charge, we can make the guilty defendant got the punishment, right? So there's a power. Because this is, you can't reject, right? How much is the power, okay? And alpha is sometimes we call significance level, right? So usually we have in the last class to talk about the confidence level or confidence coefficient is 1 minus alpha. Alpha by itself is called significance level, okay? And usually we call that often called 5% significance level, 10% or 1%. So this is usually the terminology people talk about. 10% significance, 5% significance, and 10% significance. Okay, so that is the usual terminology when you go further. So I hope I talk about this terminology because people use it without explanation because they assume you know very well. So I hope these are the terminology that you can equip yourself when we go forward. Okay. So I think I said already, right? There's a situation, there's a trade-off, right? If it is true, okay, actually you shouldn't reject. That depend on alpha, okay? You decide the alpha, okay? You decide whether you reject or not. If this is false, right, then you should reject that actually called the power 1 minus beta, okay? And I have hint already, they are trade-off between the two errors. And if you give an alpha, you can just lower beta, okay? And the rule of thumb usually just 10%, 5%, or 1%, okay? So if you increase n, you can reduce both, okay? So that's why the larger the sample, everything will be getting better, okay? So that is not surprising at all, okay? And I guess I can go to the next slide, okay? So this is the template. Actually, hypothesis testing is very like much the courtroom, right? There will be some procedure to do the job, and this procedure is rather standard. We'll keep using it, okay? So this standard way to do things, you will be learning this, okay, as we are doing examples, okay? So first, you need to state clearly what is H null and H1, okay? The null and the alternative, okay? And then you would construct a test statistic, okay, that based on sample outcome, okay, that is coming from, say, X bar, okay? We will construct a statistics called Z, okay, or we consider called T, okay? And these statistics will be used on in the first step, okay? So basically what we're doing is based on the sample you got, you calculate some number, okay? That number is called test statistics, okay, which we'll use in the next step. So basically a number coming from your sample. Okay. And there are two ways to use this number. Okay. One is compare critical values, okay, or what we call p-values. Okay. So these are the two ways you're doing it. And the idea is very simple. Okay, let me give example. So I have said that's what you are doing, right? X bar will be have mu here. Okay. So what is test statistic here? Is this guy, right, has a normal distribution with mu mean sigma square over root n. Okay. So what I'm going to do is to transform this to a z, which is normal one. Z is normal, mean 0, 1 is standardized normal. So we transform this to 0 here. Okay. And that also a bell curve. Okay. So what you're going to do, okay, is remember based on the test, all right, this should be, this area is 1 minus alpha. Okay. And you do the same here. This is 1 minus alpha. Okay. So if you still recall, this is z alpha over 2. This is negative z alpha over 2. Okay. In that particular case, if what you found, the data is here, way outside, okay, you just transform this to here. Okay. This is what we call the test statistic, right? You transform it here, right? Based on this data, you transform the test statistic is x bar minus the mu over sigma over root n. Okay, this is the test statistics. Okay, and you compare the critical value. These are the critical values. Okay, because if this is beyond these two critical value, you would reject the null. Okay, if it's within, you don't reject. Okay, so this is the method 1. Okay, method 2 is highly related. Is instead of looking at the critical value, you do the p-value, which is looking at this area more extreme than your statistics. Okay, looking at this value, is this value small enough? If it's small enough, then you also reject. Okay, actually you can see they are the same thing, right? One is looking at whether the test statistic is less than the critical value, or look at the test statistics, look at how extreme the value they are, the area. If the area is very small, then you reject. Otherwise, you accept. Okay. So, so after the break, I talk about how to operationalize this, but this is exactly the same what I'm talking. So I just basically go through the example one by one. And if you understand this graph, then you're done. Okay, basically we are done, but just we go to more detail of how to operationalize, and then you know how to work. It's not complicated. Basically, I have already said everything almost there. Okay, just follow the procedure one by one, then we're done. Okay, just basically a very simple thing because you just religiously follow step 1, step 2, step 3, and that's it. Okay, so in the meantime, let's a break of say, I guess 10 minutes. I'll go around to see if any question.
X 巴之後再用。見到咗個 view 咁你就乜講？就失控你見到個 view。咁你用呢個去左右或者等於 view 往左右嘅嗰個 X 巴嘅話是 X 巴往左行 M 排右行 M 冇公邊，咁咪等於 view 往左行 M 往左行 M 冇公邊。我個三同業界，因為我呢本呢一個嘅話，係好緊要啲嘅，都同我哋講呢個嗰每一樣。一派人都一個，一條流嘅，我覺得嗰種無頭不單，就好似阿西，好似阿西第四個。我會喺嗰一齊將我哋考試。我點解就我係做嗰題幫佢？我話曬，我哋如果係做翻，有一個聽人啦，有啲講係開人，我哋 team up 人哋我自己做，帶到兩個，我出嚟好簡單，就係基本嗰啲 data 或者啲咩，如果呢個卡佢幾多上面嘅，幾廿個 function， 基本上係都我哋做嘅，就係咁處。即係我哋揾個 data， 如果你有4個100，
Okay, so now let's get started. I guess this abstract, so we go to more concrete text, then you will realize what actually we're doing. Okay, and so let's actually see the sample mean. Actually, we are using this as a the way we're doing, right? So by normality assumption, or actually by central limit theorem, okay, this actually holds. Okay, and so the question is, okay, when we collect data, right, we just know X bar and S square, right? And do we have any knowledge about this? Okay, if we do, we call set test. If we don't, actually we don't, right? We actually t-test. Okay, and t-test will require normality assumption. Okay, only if the underlying is normal, this will be appropriate. Okay, that's very important to remind you. This is required for t distribution. Okay, So let's get started. Okay. So as we said, if we know, okay, and if under the null, okay, remember how we derive test statistic is under the null, okay, what should be the behavior of sample mean? Okay, the sample mean will have mean A. Okay, that would be something like this, right? If the sample you claim sample mean is A, there will be A here, right? That will be the bell curve. Okay, so the question is, okay, we want to know if this bell curve, we can transform this to Z, right? With this is 0, and how we transform, right? It's based on this, right? Because the variance is sigma square over n, right? So the SD, right, will be just square root of that. Okay. So by this transformation, okay, and we will see where this item, okay, Z, where it's located. If this is far away from 0, okay, then we would we would say this is not going to be supported by the data, right? If this near 0, that's okay. Okay, so let's see the example. Okay, so this is the procedure. Okay, this is standard procedure for a right tail test. For right tail means the alternative is more than. Okay, remember when you do the more than, is the violation on the right hand side has a consequence, right? This is something like the harmful substance in your food product, right? If it's more than a certain level, then you are not very happy. Okay, so that is how you do, right? That is, you first collect the data, right? X1 up to Xn, right? Simple random sample, and you can calculate sample mean, right? And you take the sample mean minus the A. This is given by your boss or given by someone, right? Some knowledge, you know, right? And you subtract from it, and you divide sigma over this root n, right? The sigma also you know, right? If we don't know sigma, that will be something we cover later, got T. Suppose we know sigma, okay? Then this is a bell curve, okay? And based on this, we either do method 1 or method 2, okay? So method 1 will be the following, okay? The Z, okay, as mean 0, right? And we will say, okay, this is alpha, this is Z alpha, okay? We're saying that we reject if the critical value is larger than Z alpha, which is a black area, okay? If the test statistic is too large, then we reject. What does that mean? Let's go back to the beginning. What do you mean by X bar? Okay, X bar here, this is A, you draw a curve. Okay, this is okay. And what actually saying is if, okay, alpha as well, if that is way beyond A, then you would say it must be more than A, right? So the same idea. Okay, let me repeat the statement. If we're trying to say we test whether the data accept whether it's A or not, right? And then when we reject this, we'll say it's way much than A. Then when we would make this a decision, right, is when we have the data that is way more than A. Okay, how's way more than A? You go to the Z, right? Because this one can transform it to a Z, right? The same thing, right? This area same as this area, right? And actually, you know from statistics, this is actually X bar plus sigma alpha sigma over root n. Okay. Okay, you can see, oh, sorry, not A, this is A, okay. A plus this guy, okay. So that is how you compare, okay. Either you compare X bar or you compare the Z, okay. But usually you compare the Z directly, okay. So this is the way to proceed, okay. This is method 1, okay. The method 2 involved in this, okay. The method 2 is very simple. Suppose this data is here, the green one, okay. And actually it's here, right? And method 1 would say you do not reject, right? Because this value is smaller than the critical value, right? Or you can look at the p-value. How to do p-value? P-value is defined as what's probability that more than what you found, that's a set, right? So look at this area, okay? This area is more than alpha, so you don't reject, right? If this is way beyond, much more, then you is smaller than alpha, you reject, okay? Say if you're the blue one, if you're here, right? The blue one, the blue area is less than alpha, right? So then you would reject. Is that clear? So if either green, you don't reject, blue, you reject, you can either compare the area or you compare the critical value Z alpha. Okay? So probably you would think it's still a bit abstract. Okay? So let's see the actual example. Okay, what we do. So consider we have a population that follow normal distribution with standard deviation 4. So basically this. If I have normal, then this also a bell. Okay. And I know depends on the sample size, the sigma over root n, right? Will be 16 over n anyway. Right? And now I have n is 64, right? So n 64, okay, and sample mean is 7, okay. So what I want to do is, okay, this is given from the question. I want to check whether it goes 6 or more than 6, okay. So the question is, under this is the first step is, once I write down this, the second step is under this assumption, assume this is true, okay. This thing will be centered at 6, right? Now, the question now is saying, if more than 6, then we reject. What do we have? Even without statistics, what you would know is, if this is way more than 6, then you reject, right? It's more than 6, you reject, right? And how can you say way more than 6 is you want this area very small, right? And how small you want is determined by alpha. Okay, we call it alpha. We will use 5%, 10%, and throughout our course, we use 5% as example. Okay, and in assignment, probably you ask more than that, but this is the number. Okay, so either you calculate p value or you use the critical value. So what we're going to do is I transform this guy. Okay, I transform this object into the Z. Okay, I into 0 here. 0 bell. How can I transform this? Right? Because this has normal distribution. Under this case, under the hypothesis, this is 6, right? And this is 16. The variance 16 over n is 64, so 64. Okay, so that is the answer. Okay, so that actually means I have Z which equal to, okay. Now we have, the thing is we have 7 here, okay. And I think 7 is like here. 7 is here, okay. and I want to transform Z to here, then what's the number here? What's the number here? Okay. How can I transform this? Is according to this formula, right? You minus the mean over the SD, okay, which is 16 over 64, because this is 16 over 64. Take a square root, okay, which is 1 over 1/2, that is 2, okay? So this is 2. Is that clear where you get 2? Okay, it's 7 minus 6 over us. This is 4, right? Over root of the n, which is 64. So this is what we have here. It is 2, okay? And the first thing is we want to do the critical value method, okay? The critical value is just Z alpha, okay? And Z alpha is 1.64. How can we get this? This is very simple. It's just the norm S inward 0.95. Why 0.95? The reason is not difficult, right? Because we want this to be alpha is the 5%, okay? That means that the other side is 0.95, okay? So you plug in this into the Excel, you should get 1.64. So let's show you Excel. Let me do the I'll just show you the norm dot S dot inverse 0.95. Okay, so that's how you get this number. Okay, so that is how I get the 1.64. Okay, is that okay? I get 1.64. Okay, so that is how you get this number. Okay, and that means that 1.64 is here. Go back to here. Okay, this is 1.64. Okay, and as that means that if our number is far greater than 1.64, then we reject. So in this case, we reject, right? Because more than that. Okay, that means that it's too unlikely that we observe this value 7, right? Because it's too large. So we would say we don't believe that mu is 6. Okay, so that's why we write in the following. It's very important how we write this one. We will say we reject H null at 5% significance level. Okay, so this is the standard way we write. Okay, is that clear? Is that okay? Don't worry, we'll do the left-hand side again, and then we'll do the two side again. So that would be, and that time you understand. So the next thing is to look at the other case. It's called the p-value method. The p-value method is very simple. It's simply asking what is the area beyond 2. Okay, what is this? And to find this, actually it's not difficult. It will be 1 minus norm dot S this 2 true. Why? Because norm this 2 true is the left-hand side area, right? So 1 minus is the right-hand side. So this at the end, I will show soon. This actually gives you this number, and this number is very small, so you reject the null. Okay, let me show you. This is actually what is number. I just go to Excel. Okay, And what I do is equal to 1 minus norm as this to true. Okay. So that's the area. This is number in the slide. Okay. Is that clear how we derive this? Don't worry, we'll be doing the left again. We do two sides again, and we do T again. We do many times. So it's impossible you don't know, because this mechanical step is very mechanical. Right? It's something like procedural thing. Is that okay? We'll do it again. Okay. Is that okay for this one? Now, if there's no problem, I erase this. We'll do it again. So don't worry. So this is the graph. Actually, I have that here. So you can see either you look at this area more than 1.64, or this area is very small, the p-value. Okay. So here I have rejection on the left. Okay. The reason is being that we do the left-hand side. Okay. And actually everything the same, right? You calculate the test statistics. Okay. But the main idea is the following, right? The X bar, the bell is like this. Under the null is here, right? The question is, you reject this one. So it means that if this is very small, right? Then you reject. If not so small, you don't, right? And how can we do it? We transform it to the Z, right? This is 0. You go to here. This area, this is same as this guy, right? You look at this, right? You can look at the negative Z alpha, right? If this is here, then you don't reject. If it is deep inside, you reject, right? And also other way is look at the area. If this area is very small, then you reject. Otherwise, you don't. Okay. So this is exactly everything is the same, but just opposite. Is that okay? It's just everything flipped to the other side. Is that okay? Now, I mean, some of you may still confused. Don't worry. You go to the example again. Then you will see the procedure is very simple. Okay. Let me show you the example. Okay. So this is almost the same question. Okay. We have a normal distribution. Okay. And the SD is 4. Okay. And basically what it's saying, if you try to draw it, right, it's like this guy, bell curve. Okay. And we have the case, this. Okay. The question is sigma is equal to, this is 4. Okay. And now we have n is 64. Okay. And sample is 5. Okay. Now you're given that this mu is 6 or less than 6. Okay. We're not explaining why this case is given. So basically the idea is, say I want to test the good substance, the active ingredient there, it cannot be less. If the medicine less than that, then the medicine is basically useless, right? So under the null hypothesis, under our working hypothesis, this is 6. Okay. So we are saying that we're trying to see the data is going to support our alternative, right? It's going to say anything. So it's small enough, then it's going to be a rejected null, right? So what we have the data is 5. Okay. So the first thing is, if you have a 7, then you're done. You don't need to do anything, right? If a data say 7, then we're done. We don't need. We just go home, right? So now the data is 5. Then we need to worry. Okay, so it's 7 is here. Okay. So the question is this? Sorry, it's 5. Okay, it's 5 now here. So the question is it 5 very small compared to 6? Okay. Is the distance very small? Okay. Then the question is asking, is this area, right, smaller than alpha or bigger than alpha, right? So that's actually this area we call p-value, right? This value we call p-value. is this p-value smaller than alpha or not? If smaller than alpha, then it's very small. So that's the idea. Okay, the question is, alpha is less than p or not? Okay, and what we're going to do is look at the bell curve. We transform it to z, right? Here, this is 0. Okay, and transform. What is 5 going to be here? Okay, is you're going to subtract the 6, right? And over sigma, okay, over root n, right? That is because this is the variance is sigma square over n, right? So that's over the SD, right? And that actually gives you -2. Okay. So there are two ways to do it, right? We can calculate if this is alpha, okay, that is -z alpha, okay, and -z alpha, set alpha is 1.64, okay, and because 5% here, right? So either you can just simply do the norm, okay, as inward 5%, okay. Actually, this gives you -1.64 because norm as inverse gives you the left area. Right? If you give left area, you give you the number, right? Or you can take norm as inward 0.95 and take take a negative value, right? So either way will work, right? Either this is the 9.95 and you take the negative value, or you can just norm as inward, okay, 0.05, okay, and also give you because symmetric, so either use one way or the other to give you the same answer, right? The symmetry. Is that clear? So what you have here is the critical value is -1.64, and you are more extreme than the critical value, then you reject the null. Okay, because it's too far away, too low before compared to 0, right? Much smaller than 0. That means that 5 is much smaller than 6. Then you would say the data support the idea less than 6. Is that clear? Okay. So the other way around is, as I said, use the p-value method, which is asking this area. Okay. Calculate this area. Okay. How can you calculate this area? Right? It just this area. It just norm as this, right? Because this is calculate area, just -2. Okay. That will give us 0.0028. Okay. So that is less than 5% is very small. So something extreme is happening. So you would think that is not possible. Okay. So let me go to the Excel to prove that's true, right? That is the norm as this -2. Okay. Also, I have to put true. Okay. Sorry. Okay. So that is the case. Maybe I have to. Okay. I have to be careful here. I forget the true here. Okay. Well, this is pretty much how we do hypothesis testing. Is that clear? So you can see the procedure exactly the same, but we just have to be careful. But the idea is very same. It's like, is it sufficiently smaller than the mean, right? When you compare how is small or big, you look at the probability. Okay. But do remember it's same as if you try to construct the confidence interval, okay? Then your interval will not include 6, okay? So you can check 5 plus minus, okay? Because interval, right? This go to 5, and this is a Z alpha sigma over root n. Okay, you can actually solve because this is actually half, and C alpha is 1.64. Okay, and you can solve. Okay, this one when you draw, okay, it is less than 6. Right, when you go left by this, go right by this, it doesn't include the 6. Okay, so if you do interval estimation, actually you will not include 6. Okay, so that is the idea. Is that clear? Is that okay? Okay. If okay, then let's go to the next one. Okay, this is the graph. Okay, the next one is very similar. Okay, if you know how to do one-sided, each side, then two-sided will be similar. The idea is again the same. We have X bar here. Okay, under normality we have a bell. Okay, and assume this is true. Okay, the center is A. Okay, and we are talking about we need a absolute accuracy. More than or less than not allowed. Okay, and what you're going to do is you have a symmetric distance. Okay, if it is too less or too much, then you will reject, right? And you would not be very happy, right? It's too big or too small, you are not very happy. Then how can you talk about too big or too small? We'll talk about inside is 1 minus alpha, and these two area is symmetric, so alpha over 2. This area is alpha over 2. Okay, and if it is beyond these values, then you would say no, right? So if you're able to transform this to the set, right? This is 0 here, right? Here we want 1 minus alpha, right? And this is alpha over 2, right? This is alpha over 2, right? And by construction, this is Z alpha over 2, and this is negative Z alpha over 2. So depending on your data, right? If your data fall within the red region, okay, and that will of course fall within the orange region, right? Then you reject, right? Otherwise, you keep what you want. Is that clear? Same as what we have. But here is okay. So here I have only one tricky thing I have to talk about is the p-value. Okay, this guy is super tricky. What about p-value when two-sided? Okay. Okay, and the reason is the following. If I got a value here, okay, but obviously you'll reject, right? Because the area look like this, right? Okay, this area, okay. You would want to compare this area to alpha over 2, right? You compare this area to alpha over 2 because either it's this side or either this side, right? You actually compare the tail area, okay? The tail compared to the tail area, is it less than alpha over 2? Okay, if this is the case, you reject, right? That means that 2 times this tail is less than alpha, okay? And that the 2 times the tail is the p-value. So that is why 2 times this value, we compare to alpha. Is that clear? So the p-value has to be multiplied by 2 because 2-sided, you're comparing with alpha over 2 rather than alpha. So that's why when we do p-value, you times 2. So this is the only tricky part that you have to be very careful. Okay, if you compare critical value, everything is very straightforward. But p-value for 2-sided one, you have to multiply by 2 because by convention, actually compare alpha over 2, but you just multiply this. That's called p-value. Is that clear? Okay. So let me go over the, no question, let me go over the example. Okay. This example is the same, is very familiar. Okay. You should be the question like this. Okay. Again, we have something a normal distribution. Okay. So that means that the sample mean is also a bell curve. Okay. And we have sigma is equal to 4. So this is given. Sigma is 4, which is good. With a random sample, okay, of n64, x bar is 5. The sample mean there. Okay. Now our null is given is 6. Okay. Now it's 6. So that means that this thing, if this is true, 6 is here. Okay. And what do we find from our data? Okay. Our data is 5. It's somewhere here. Okay. The question is, of course, 5 is different from 6, right? There you when we have to decide whether 5 is enough different from 6, right? Of course, if your data is x bar 6, then you can go home, right? Now the problem is less than 5, less than 6, right? So if x is actually x bar negative 100, then probably you would just say you're done, right? Because so far away. But now it's not so far away, you're not clear what's going on. Okay. So because what you're doing is a 2-sided one, okay. So that means that I would be saying that this area, okay. I don't know if this area is included, but anyway, this area, okay. We want it 2.5%, okay, 0.25, okay. Because I used 5% on both sides, that together is 0.25, okay. So I would say if this is beyond this, I don't know whether 5 is here or not, right? Okay. But turn out to be here. If it's this one, then you reject. If this one, you don't, right? And note that is you decide this before you do the sample, okay? So we actually don't know whether it's 5 or it can be 7, okay? So we don't really know, okay? Because you decide the hypothesis before you do the random sample, okay? So now how you proceed is you just transform it to Z, okay? And 6 here is 0. You still have bell curve here, okay? And you want this area, this 2 area is 0.025, okay? And okay. And now you want this number go down first, okay? What is this number? What is number? Okay. The transformation is here. You minus the mean, right? Over the sigma over root n. Okay. That means it's -2. Okay. So we want to know what should be this guy. Okay. Is this guy here or here? I don't know. You have to calculate. So how to calculate this, right? It's very simple. As area, I want to go back, right? So you can do norm S inward. You can use this 0.025, okay? This should give you -1.96. Okay, let's check it out. Okay, you can do norm as inverse 0.025. Okay, so negative 1.96. Okay, so that is how I get this number. Okay, of course, if you don't like what I'm doing, you can do the another case, you do 975. Okay, this gives you the positive one, but you just take a negative, right? So what we have is negative. We figure out, okay, it's actually is 0.025 actually is like here. Okay, it's deep inside. So this is negative 1.96. Okay. So as you see, negative 2 is much less than, it's less than 1.96. Okay. So that's why we reject. Okay. Of course, if you get the number is negative 1.6, then you don't reject. Is that okay? So in this case, we reject. Now here comes to the, okay. So as you can see, if the X bar, right, is very close, is 5.9, right, then this one will be much closer to 0, right? Then you don't reject, right? I think that is easy. I didn't to solve. So the last thing I want to show here is about the p-value, right? P-value. So how to do p-value here? How to do p-value? Okay. The p-value is this area times 2. Okay. So how do you operationalize Excel? It's just like this area comes from 2, so that is the norm as this negative 2 true. Okay. But you need to multiply by 2 because you care about two-sided, right? Because you don't know which side before you do it, right? So end up in this, you need to multiply by 2 because two-sided. Okay. And because you actually compare with the alpha, not alpha over 2. So that's why this is the convention. Okay. So let me show you the Excel. Okay, in case you would be interested in knowing how I get the number. Okay. So this is less than 5%, right? So you would reject. Is that clear? Okay, so you can easily see that because the 5 is far away from 6, so that's why the number is more than that, right? But if your number is 5.5, 5.9, 5.8, then you don't reject. Right? You can easily see that. I don't think I need to repeat the calculation. Is that okay? Is that clear what we are doing? Is that clear? Any question? So for the remaining time, I'm not going to open a new thing, but I will try to hint what we are doing. Okay. So just use 2 minutes to talk about what we are doing, right? So I'll summarize what we have done. Okay. So far, what we are doing is with H now, mu equal to A. Okay. Based on this, we can construct X bar is a bell curve. A is here, right? And depends on X1. If it is mu more than A, then you would have see if this area, this is alpha, right? And if you have H1 is mu less than A, you would have this alpha, right? And after that, you transform this guy to the Z, right? Z zone. Okay. And what you're doing is look at if this Z alpha, if beyond to the red area, you reject. Otherwise, you don't, right? Same as if you have the blue one, sorry. The blue one, if alpha, this is negative Z alpha. If the blue, you reject, right? Actually, these are called, this area called rejection area, right? And you can do the p-value the same thing, right? And in the case where H1 is mu not equal to A, right? Then what you do is a little bit more tricky. Then you have this and this. This area is alpha over 2, and this area are alpha over 2, right? And this is Z alpha over 2, and you have area this Z alpha 2. Okay, these are all the rejection areas. Okay, and how do you transform this, right? Z is coming from X bar minus mu sigma over root n. Okay, and easily you can imagine next class we'll talk about T, right? Will be just the same thing here as over root n. So everything the same. Instead of a Z bell, use T bell, and that's it. Okay, that we will cover next class. But so far, this is what we're going to do. Okay, so I will see you next week, and that remember your submit your assignment. Okay, have a nice day. area 佢分開嚟就拗嘅。如果係咪睇落我話嗰啲零問題做咧？因為你話佢嗰個佢零問題做，唔係有冇做？一定係會嘅啫。OK，好，明白。